Welcome back, College Chem. We are looking at our quantum numbers today. And I think as I reflect back, I think the reason why students sometimes get a little concerned when it comes to quantum numbers is because it just sounds so foreign to us when we start to think about these little tiny particles and how we start to describe them. But at the end of the day, quantum numbers are still just electron configurations. If you remember, there's four things we need for an electron address or location. We need an energy level, a sublevel, an orbital, and a spin, right? We need four things for us to be able to say, here's our highest probability to find the location of an electron. And that's all that quantum numbers are as well. So we're going to use some slightly different terms, but end of the day, trying to get back to that same spot. So going to be looking at a little bit of vocab here, kind of reviewing off of what Professor Dave, I think, was saying. But there's really four kind of quantum numbers we need to be familiar with. The first is our principal quantum number, right? Principal, nope, wrong principal. Principal, quantum number. And all that's describing is your energy level. This is the broadest kind of number we can use. It's often identified with N, which is the same as our original quantum electron configurations. And it's going to be just a whole number value, a whole number integer, starting with energy level 1 and working its way out. And so this is just telling you what energy level you're on and describing kind of the general size of our electron orbitals. Our second address piece, we're going to call it our angular momentum. Angular momentum is given the symbol L. Given the symbol L. And this is really referring to kind of the sublevel or the shape at which we're going to kind of describe the location of our electrons. And so our L value is going to start with kind of 0 and work our way out. It's always going to be from 0 up to n minus 1. So you'll always be one less than whatever your n quantum number happens to be. So there's kind of our shortcut n minus 1 when we're describing, but it's still going to be some whole number integer. It's got to be from 0 to 1 less than what your n value is. Our third kind of principal quantum number value is our magnetic quantum number. And that gets the symbol M sub L. The reason we do M sub L is because it's going to be your L value from negative to positive value. So that's going to be negative L, including 0 to positive L. And really, this is describing which specific orbital our different electron might be found in. So really, we're still principal quantum number, that's the energy level. Angular momentum is telling you what shape it's going to take or what sub-level shape it's going to be. Still describing kind of S, P, D, and F kind of shapes. Our magnetic quantum number, or M sub L, is describing which specific orbital that it's in, because if you have more than one orbital in there, you got to tell which one it's in. And then your last one is your magnetic spin, which is the same as what we saw with our original electron configurations. That gets the symbol M sub S, and that's just going to be either a positive or negative 1/2 value. We say if it's a clockwise spinning, it's a positive 1/2. If it's counterclock spinning, it's a negative 1/2. If some of you remember back to kind of Chem 1 when we did these, sometimes we would do just little half arrows. And that's because when we mathematically derive or mathematically express our quantum numbers, it's a positive 1/2 or negative 1/2 value. And so just like we saw with our electron configurations, if you have 4 quantum numbers, there's only one electron you could be referring to. That's it. And so it's kind of nice because there's actually, just like we saw with electron configurations, there's kind of this pattern on the periodic table. There's still a pattern on the periodic table for our quantum numbers. We say that for our principal quantum numbers. So I'm going to do that one in red. Ooh, that is way too big. Make it a little smaller here. I'm going to do this one in red. For our principal quantum numbers, it's just the energy level. And on the periodic table, our energy levels for our main group refer to the rows or the periods. So if we're thinking about our N's for going across for S's and B's, it's just going down the side here on the periodic table. Now, the D's, if you remember, our offset one. they start kind of, so here's n equals 3, n equals 3 for the D's. Here in the middle, n equals 4, n equals 5, going across the middle transition block here, n equals 6. And then the F's actually don't start until n equals 4. So this first row kind of going across is going to be n equals 4. This bottom row, n equals 5, depending on what element it is you're describing. But for our main groups, it's just what row you're in. So again, 1, 2, 3, 4, 5, 6, 7 going across here. So just n describing kind of the principal quantum number, the general size. This is your energy level. Just give it a whole number. Your angular momentum is telling us what shape are we going to see these electrons start to form? Is it a sphere? Is it a peanut? Is it double peanut? Is it a flower? That's our angular momentum. And so we can describe that using one less than our kind of current energy level or quantum number. And so for our S area here, let me change my color here a little bit. We'll call that our blue. For our S's, our angular momentum, it takes kind of the shape of a sphere. For our far right column, our L will always equal 0. L equals 0. For our peanut area over here, far right, N's going to equal 1. N equals 1. For our double peanuts here in the middle, N equals, sorry, not N, whoop, 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 back it up, back it up, back it up, L. L equals 1 for the peanuts. L equals 2 for the double peanuts, for the d orbitals or the d sublevel. And in the bottom row here, L would equal 3. So just describing the general shape that we're going to see for those kind of orbital shapes is our angular momentum. We call it the angular momentum. And these are all statistically kind of probability derived. We don't actually know. We just say based on their charge and how they have to arrange themselves in three-dimensional space, here's the shape they're most likely going to take. Magnetic quantum number is where we get specific. We say, okay, which shape is it actually in? Which of the orbital pairs is it actually found in? And if you remember, Hund's rule becomes really important when we start to look at how our electrons physically fill around our, I should do yellow, that's going to look not so nice. So for our magnetic quantum numbers, we're going to use our kind of negative to positive L value. And these are just telling us exactly which orbital we're in. So if we're thinking about like, I don't know, that 2s, well, there's no choice here. It's one sphere. So your L value, oh, L was 0 right here. So your M sub L would also equal 0 for anything in that first column and anything in the second column, because those first two electrons have to pair up in that first sphere. So from 0 to 0. Yeah, okay, cool. For our peanuts, if you remember, there's 3 p orbitals. We've got a peanut that goes, ooh, let me see if I can find some room. I'll put them up here towards the top. Oh, that's going to be behind where you are viewing my screen. I'm running out of space here. If you remember, there's 3 peanuts, one going up and down, one going side to side, one going front to back. And Hund's rule says they spread out. We're going to fill one at a time, and that's until we have to pair up. And so we just give these a value. We would say that this first peanut is the M sub L -1. The second peanut is the M sub L 0. And that last peanut is the M sub L +1. So we're going from negative L to positive L. Well, if you're working your way across kind of the P block where you've got first 3, they all split apart, and then the second set of peanuts then have to pair up, that means there's this pattern on the periodic table. We know that for this first one, we're going to fill in the -1 peanut. Then we'd fill in the 0 peanut, then the +1 peanut. If you want to put the 1 plus, sure, not going to hurt anything. And then they go back and pair up. So then our fourth electron would have to go back into the -1. Our next goes back, partnering up that second, and then we fill in that very last peanut. If you're thinking about your arrows, right? We said these were the peanuts, right? We're calling this the -1. This is the 0. This is the +1. Remember, our arrows fill one at a time, and then we buddy them up. And we see that pattern as we go across the periodic table as well. I want to show you all the patterns, and then we're going to look at some examples. So if you're sitting there going like, what the what? Hang in there. It's going to make sense. I promise. It's not like the first time we learned electron configurations and it didn't really make sense until we put it all together. So I'm getting you all the parts you need, and then we'll come back and look at it. For the D block, then we're going from -2 to +2, from negative L to positive L. So if we're going across that D block, I'm just going to pick a row that hasn't had any writing in it. Our first electrons are going to go in the -2 double peanut, then the -1, then the 0, then the 1, then the 2, positive, positive. First ones all fill individually, and then we go back and we pair them up. So then we go back and do our -2, our -1, our 0, our +1, and then our +2. You'll notice we filled up all of our electrons. By the time we get all the way through to that second +2, all of the d orbitals are filled. We filled every partner pair going across. Down here at the bottom, we would start then at -3, -2, -1, 0, 1, 2, 3. And then, sorry, nope, not that. Go back one. And then we repeat. We fill up our -3, -2, -1, 0. Sorry, let me erase my scribbles over here from before. +1, +2, +3. So again, we're just coming up with a system to keep track of our electrons. Cool, then spin. Spin's pretty easy. It's either going to be +1/2 or -1/2. What haven't I used? I haven't used purple. Let's do purple. Purple's a fun color. So we'll do spin in purple here. So we would say that for our first electron in this s orbital, just by convention, we do our positive values first. Then we do our negative values. So anything in the first column is going to have a +1/2. Anything in the second column is going to be a -1/2 for our S block. Over here for the peanuts, by convention, we do the up arrows first. So we're going to have +1/2, +1/2, +1/2. So all of our positive spins go in first. And then when we buddy them back up, they got to be different somehow. Counterclockwise spin for that second half, filling back into those p orbitals. Going across then on our D block, we'd have +1/2, +1/2, +1/2. How fast can I do this? +1/2, +1/2. So the first 5 electrons all fill individually. And then we go back and partner them up with -1/2, -1/2, -1/2, -1/2, -1/2. And now we filled up all of those double peanuts, right? We've got 2 in each. One has a positive, one has a negative spin on it. And then going across the bottom, we'd have +1/2 for the first 7 electrons. And then we would go back and fill in our -1/2 values. Oh my goodness. But again, we're still describing the same thing. If we have all 4 numbers here, we're still describing the energy level. What shape is the kind of electron field going to be in? That's our sublevel. We've got our quantum number. That's which shape specifically is it in? And then we've got our spin. Which direction are those electrons actually spinning in that particular orbital? If you have all 4 parts, there's only one kind of electron you can be talking about. So for example, if I were to look at 2 outermost electrons. So for example, just so that we can see how this would actually be written if you were to actually write these out. So let's say we're going to look at, sure, why not? I should pick a different color. Let's say we're going to look at, we'll do kind of a yellowy orange, these 2 electrons right here. Your outermost electrons for these 2 different areas. I'm going to erase so that's a little cleaner for us to see what's going on here. If I was to describe, in this case, if I look in the periodic table, do I have one handy? 1, 2, 3, 4 down. So for potassium, my first, let's see if I can match my colors here. My first principal quantum number for potassium is just the energy level. I'm in energy level 4 for this electron right here. I'm in the S sublevel, which gets the L value or angular momentum of 0. It's going to make kind of a spherish shape, 0. Well, there's only one orbital. And so that also, in terms of which orbital it has to go into, it doesn't have any choice. It has to go into the 0 orbital. And then if it's the first electron to go in there, we say by convention, it's the positive 1/2 value. Oh, I was going to color code those, but then I didn't. If I wanted to compare that to the element immediately below it, the outermost electron for rubidium, the only thing that's different is we're in the 5th energy level. It's still in the S sublevel. It's still in the first S sphere. There's only one of them. And it's still going to, by convention, be the positive or clockwise electron for that first electron. So you'll notice everything is the same here, and that makes sense. It's in the same column. It's the same outermost electron. It's just, it's one additional energy level higher. If we were to describe, say, the one right next door to potassium, sorry, this is a good example. We'll keep rolling with it. If I wanted to describe our element right next door, so we'll sneak it in here. Right next door, we got calcium, right? Calcium. We can't count down. It's still in energy level 4 for our calcium here. Sorry, I'll do it all in black so it's consistent. It's 4th energy level. We're still in the S sublevel, right? So its angular momentum would still be 0. There's only one orbital that could be. We call it the 0 for its magnetic quantum number. But now it's got to be spinning in the other direction. So its spin would be a negative 1/2. And if you have all 4 of your quantum numbers, there's only one electron you can be talking about. Cool. So let's look at some more examples here. Let me pull up a different periodic table. It's got some elements on here for us to compare. And I want to share a different screen. I want to share this one over here. Cool. Let's take a look at this one. Burp, 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 burp. Cool. So if we were just to look at a couple examples. So phosphorus. Let's do phosphorus. Hit the little button here. If we're looking at phosphorus here, we count down. We're looking for 4 numbers to describe the outermost electron for phosphorus. We count down. It's in 1, 2, 3rd energy level. So N would equal 3. So here's your N, energy level. It's in the 3rd energy level. For our angular momentum, L, it's in the P block, right? So it's going to be our P shape, our peanuts, just describing the shape of the field. Our peanuts get the L value of 1. Now, there's 3 peanuts we can have, and they're going to get assigned a magnetic quantum number, M sub L, of -1 to 1, and they fill one at a time. This is our -1. This is 0. This is our +1. So this would also get a 1. We're in that 3rd peanut is what this is saying, essentially. We're in the 3rd peanut, and it's the first electron to go in there. So for our magnetic spin, we by default, by convention, say it's a positive 1/2 value. These 4 numbers combined tell us it has to be this outermost electron for our phosphorus atom. Another example, let's take a look at cobalt. Sure, why not? Cobalt. Oh, that's in the 3rd energy level. Remember that? Sorry, that's in the D block. Remember that the D block starts in the 3rd energy level, right? We don't see the D's until the 3rd energy level, which means our principal quantum number here is going to be 3. In that 3rd energy level, our D orbital, S's are 0, P's are 1, D's get our L value of 2. And now we can go from -2 to +2. We got negative, -1, 0, 1, 2. Then we repeat, -2, -1, 0, 1, and then 2. We're in the, it's our -1 M sub L. And now we need the spin. If you're paying attention, we've already filled the first one. This is our second -1 orbital to fill. So this would be a negative for the second one here. Sorry, I'm touching the screen with my palm. -1/2 for that final quantum number. And again, from these 4 numbers, there's only one electron we could be talking about. And so really what we're doing is we're taking both our electron configurations, our orbital notations, we're combining it all down to have 4 numbers represent the location of our electrons. Cool, one more for you. Let's look at strontium on here in terms of just assigning the quantum numbers. Then we'll do one more going in reverse. If we count down, it's in 1, 2, 3, 4, 5th energy level for our primary principal quantum number. 5th energy level. It's in the first kind of area on the periodic table. That's the S block. Well, that gets an L value of 0. M sub L has to go from -L to +L. For 0 is still 0. It is the second electron to go in there. So it is the -1/2 spinning magnetic spin electron for that s orbital. And so again, these 5 values together give us then our electron configuration. Let me do a reverse. Let me erase that real quick. I'm gonna make this one up. We'll see how we do here. I don't know, might fail horribly. I'm gonna say our n equals 2. Our L then can go from 0 to 2, right? Sorry, can go from 0 to 1, 1 less than the n. We'll say it's 1 for the L. So then M sub L can go from -1 to +1. I'm going to say it's 0. And I'm going to say it's a +1/2. I'm just making this up a little bit. We'll see what we get. All right, energy level 2. So 1, 2, second energy level. L is our second shape. So that's the peanuts. Means I'm somewhere over here. I'm 0. So I got -1, 0, +1, -1, 0, +1. So if I know my M sub L is 0, that means it's either going to be this carbon or this fluorine. I look at my spin, and my spin is a +1/2, so it's the first element to get, or the first electron to get filled in. It hasn't been paired up yet, which means it has to be then the electron configuration or quantum numbers for carbon. Just think about how we would work backwards if we were given our quantum numbers. Cool, we'll be getting some more practice as we start to look at these principal quantum numbers and our quantum numbers for electron identification. But hopefully it gives you a good overview of how we can use this periodic table, which we know is a great tool to be assigning these quantum numbers.